Hello, welcome back to Educator.com and welcome back to Physical Chemistry. So in the last 4 lessons we've been discussing vibration spectroscopy, rotational spectroscopy, vibration rotation spectroscopy. Today we're going to talk about electronic transitions. So let's get started. Okay, now diatomic molecules, let's go ahead and do blue today. Excuse me. So diatomic molecules absorbing radiation in the visible ultraviolet range they experience transitions to excited electronic states. Okay, so we call these electronic transitions. Electronic transitions. It's where we send the electron actually up to a higher level of energy. Now, electronic transitions, do you remember when we did vibrational transitions? So we had just those rotational transitions, that's in the microwave range. In the infrared range, we had vibrational transitions, but with the vibrational, you got the rotational also. With electronic transitions, you get the vibrational and the rotational also. So electronic transitions are accompanied by both vibrational and rotational transitions. In general, the rotational transitions we're not going to worry about because they're reasonably insignificant. It's the vibrational transitions that we're going to be concerned with. Now, very, very important, each electronic state has its own potential energy curve. That's what you see here. This is the ground state. This is the first excited state. Or they say E1. It could be any of the excited states. Anything above the ground state has a potential energy curve. It has its own set of vibrational energy states. And the excited electronic state, this one right here, the one on top, it has its own set of vibrational energy levels. So each electronic state has its own potential energy curve. Potential energy curve. And they don't necessarily need to look alike. Okay, one is not a copy of the other. It might look like it here, but they're not. Okay, now, let me see, should I do it on this page? That's fine. The total energy then of the molecule of a diatomic molecule, leaving off the translational energy, leaving off the energy of motion. And we're just going to be concerned with the electronic energy, the vibrational energy, the rotational energy of the molecule is E total. Well, it equals the electronic energy plus the vibrational energy plus the rotational energy. That's simple. Okay, E total equals E electronic plus we have nu sub E times R plus 1/2 minus x sub E nu sub E times R plus 1/2 squared. This is the vibrational energy under the anharmonic oscillator. plus b times j plus 1 minus d times j squared times j plus 1 squared. Excuse me. This is the rotational energy, the non-rigid rotator that accounts for the centrifugal distortion. Okay. This one right here. E, electronic, is the energy at the minimum of the potential energy curve of the potential energy curve. In other words, in the ground vibrational state, it is that energy right there, whatever that happens to be. In the first excited state, it is that right there. Okay? So it's the energy at the minimum of the potential energy curve. That's what the electronic energy is. Okay. Let's see. Curve transitions between vibrational states. All right. Now, transitions between the vibrational states during electronic transitions, in other words, during the transition from one electronic state to another, are called vibronic. Called vibronic transitions. Now, in general, we will ignore the rotational term. In general, we will ignore, like we said before, the rotational term, so it makes our equations a little bit easier to deal with. Ignore the rotational terms. Rotational terms in the above equation. Okay. And the reason is because on the scale of electronic energies, well, we're talking about, 10 to the negative 18 joules. The rotational energies are insignificant. The rotational energies 10 to the negative 24th joules are very small. So for the most part, we can just ignore them. Okay.